Testing microphone. Testing microphone. Testing. All right, welcome back to episode 6, side channel analysis with the ChipWhisperer Nano. In today's episode, we are going to focus on part 3 of the side channel analysis 101 notebook, which covers large Hamming weight swings. This lab references training material located on the main ChipWhisperer website. In the previous part of the course, we saw that a microcontroller's power consumption changes based on what it's doing. In the case of a simple password check, this allowed us to see how many characters of the password we had correct, eventually resulting in the password being broken. That attack was based on different code execution paths showing up differently in power traces. In this next step of labs, we'll posit that not only does different instructions affect power consumption, the data being manipulated in the microcontroller also affects power consumption. The learning outcomes for this lab, using a different power measurement to validate a possible device model, detecting the value of a single bit using power measure, and breaking AES using classic DPA. First thing we're going to do is navigate to our ChipWhisperer directory and activate the Python virtual environment. We're going to then launch the Jupyter Notebook server. We're going to go to the Jupyter folder, go to the courses folder, SCA101, and we're going to go to the main notebook for this lab. Large Hamming weight swings. Before we continue, we'll want to check that we've done the following tutorials. We have done the Jupyter Notebook intro. We have done the side channel analysis 101 intro, and let's see, the part 2, you should have understand how power consumption changes based on what code is being run. We did that in the last episode. For power trace gathering, at this point, you've got to insert code to perform the power trace capture. There are 2 options here, capture from a physical device or read from a file. We're going to be capturing from a physical device. And I'm going to open up the hardware notebook for this lab to complete that aspect of this experiment. Be sure you get OK to continue. All right. I'm going to go ahead and check out what we did in the main notebook for the last project, because I believe we included some modifications to the existing Python or in the code blocks. And as we can see, there are still our previous message logs from running some of the Python blocks. So one of the things that we integrated was this text cell, hardware integration notebook. We incorporated configuration, generic setup, firmware build, and device programming code that basically helps us with these kinds of steps. So we're going to want to change the scope type to nano. So let's go ahead and do that. We're going to change this to CW Nano. We're going to change this as well to CW Nano. Tiny AES 128. I believe that is what we're going to want to use as a crypto target. But I want to verify that. So in prior notebooks, we had set the crypto target equal to none. And I just want to validate that's what we're going to be doing here. Crypto target set equal to none. But the issue I'm having is that it's already set to some kind of default setting, and I forget exactly which one we want to set it to. Crypto target. I want to look for where it says tiny AES. Sorry. I'm going to do a little bit of research here, so bear with me. Yeah, I'm not sure where that lived, the crypto targets. Which is unfortunate because I'd really like to know. All right, here we go. All right. So, completing courses. All right, these are typically used as follows in the tutorial. Scope type indicates the capture hardware to use. If you have a ChipWhisperer Lite or Pro, use Open Analog to Digital Converter. If you have a ChipWhisperer Nano, use CW Nano, which we're using in this current lab. Platform selects the target we're attacking. As of ChipWhisperer version 5.1, tutorials only support at most CW Lite ARM and Nano, which we're using. So we're going to set scope type to Nano, platform to Nano. For crypto target, this selects the cryptographic library to use on the target. If unsure, use AVR crypto lib for X mega target and tiny AES 128 otherwise. Tutorials that don't have this block or use none don't require a crypto library. All right, so for our current experiment, it's already using AES 128C, so we're going to want to go ahead and just leave it to that way. So let's go ahead and go back. So we have our main notebook for large Hamming weight swings. We have a hardware version. First, you'll need to select the hardware setup you have. You'll need to select a scope type, a platform, and a crypto target. Crypto target selects a cryptographic implementation with tiny AES working on all platforms, which is what we're going to continue to use. And looking in the main notebook, we already have that set up here. Let's go ahead and run this cell block. The following code will build firmware for the target, which is the run block. Go ahead and run that. We're getting some issues here. Could not find ChipWhisperer. So let's restart this kernel. I'm going to unplug the ChipWhisperer. Wait a couple seconds. Gonna plug it back in. Go ahead and run that first block, and now we're going to run the second block. Found our ChipWhisperer. All right, let's look at this next one. Go ahead and run this first bash block. This is the build log for the make command. Looks like everything is working successfully. We see that our CW Nano platform was built with the target being the STM32 F030 with the crypto target set to tiny AES 128C and the crypto option set to AES 128. We go ahead and execute this program target block, which is going to program our STM F32 device. The thing we want to test here is how Hamming weights affect the power trace. So before we continue, let me go ahead and look up what a Hamming weight is. The Hamming weight is named after the American mathematician Richard Hamming, Although he did not originate the notion, the Hamming weight of binary numbers was already used in 1899 by James Glaisher to give a formula for the number of odd binomial coefficients in a single row of Pascal's triangle. The number of odd binomial coefficients, Glaude's sequence, is an integer sequence named for Henry Glaude or Gold that counts how many odd numbers are in each row of Pascal's triangle. In mathematics, Pascal's triangle is an infinite triangular array of binomial coefficients, which play a crucial role in probability theory, combinatorics, and algebra. The row of Pascal's triangle are conventionally enumerated strings with row n is equal to 0 at the top. The pattern of numbers that form Pascal's triangle was known well before Pascal's time. The Persian mathematician Al-Kharaj wrote a now lost book which contained the first description of Pascal's triangle. In Pascal's triangle, each number is the sum of the two numbers directly above it. That'll be 4, 6, and then 4. Okay. To get as big a swing as possible, we'll convert all the first bytes we send to be either 0 or 8. 100 traces should be enough to see a difference. We're capturing 100 traces. We got the OK to continue. So let's proceed. As we've seen in the slides, we've made an assumption that setting bits on the data lines consume a measurable amount of power. Now we're going to test that theory by getting our target to manipulate data with a very high Hamming weight and a very low Hamming weight. For this purpose, the target is currently running AES and encrypted the text we sent it. We're correct in our assumption. We should see a measurable difference between power traces with a high Hamming weight and a low one. Currently, these traces are all mixed up. Separate them into two groups, 1 and 0. Here's an example of how we use the first byte to check for a 0 and assume if it's not that, it's 0xFF. Here's a simple iteration to print them. Now extend this to append them to two arrays. So we want to create a one list array and a zero list array. Here's one list, here's zero list. That means we're going to have to create an array. We can do that simply by initializing on list equal to the brackets. How to initialize an array in Python. Initialize all the 10 spaces with 0. Empty list, which is not null, just empty. So that's what we're doing. Okay, so we've created our empty arrays. Non-null. So we wanted to create the arrays. Now we need to loop to append the two arrays. How to traverse an array in Python. Python loop through an array. For x in cars, print x. Okay, so for z in for z in zero list, well, our list is empty. So we want to we have a trace array. It should be added to zero list. So text in array. So the length of our trace array. I think I could take this. So for I in range of the trace array, if text in array is equal to this, else. So what we're going to want to do here is set zero list of whatever element that is, which is I, and we're going to set that equal to 0. And then here we're going to set one list equal to 1. Right? So I'm just going to do a quick check to see if we had completed a successful implementation. I'm not too familiar with Python. I'm somewhat familiar with it, but definitely need a little more practice. Okay, so the issue You're assigning by index into two empty lists. I think the reason it isn't going to work is just because this statement here. I mean, I've got the right idea. So instead of setting zero list of some index equal to 0, we're going to call zero list dot append trace array of I. So it's going to append the value. So it's just going to add on another element. Okay. On that block. We should have two different lists. Whether we sent 0xff or 0x00 was random. These lists likely won't be evenly dispersed. Next, we'll want to take an average of each group. Make sure you take an average of each trace at each point. We don't want an average of traces in time, which will help smooth out any outliers and also fix our issue of having a different number of traces for each group. The easiest way to accomplish this will be use the np.mean function, which can take a list as an argument. You'll need to specify the access parameter as well to ensure you take the correct dimension. Check the resulting size to make sure you still have traces of the same length as one input. The following block shows you how you can verify that, assuming you used one average as the average. Finally, subtract the two averages and plot the resulting data. I think that's because we're missing an import statement. We need to incorporate matplotlib. There we go. You should see a very distinct trace near the beginning of the plot, meaning the data is being manipulated in the target device. In the target device is visible in its power trace. Again, there's a lot of room to explore here. Try setting multiple bytes to 0, and I believe I think the 0x00 and 0xFF, there's something I could refer to them as 0 and F are single byte values written in hexadecimal. Decimal value for 0x00 is 0, and decimal value for 0xFF is 255. In binary, the 0xFF is all ones, all bits are 1, and in binary, 0x00 is all bits are 0. So we have the minimum possible value and the maximum possible value. In our ChipWhisperer lab, they set a plain text byte randomly either to all possibles, all 0, and or all 1. Hamming weight swings between 0 and 8 bits set, creating a large, easily visible difference in your power consumption. That's what makes the spike stand out in the difference of means trace near the start of the plot. Okay, try setting multiple bytes to 0x00 and 0xFF. Try using smaller Hamming weight differences. Is the spike still distinct? What about if you capture more traces? Okay, so is it suggesting that we make modifications in here? Let's explore some of the possibilities it suggests. If you want bytes 0 through 3 to flip altogether between 0 and FF, change the loop body like this. For I in Trang, N description capturing power traces, set the scope arm with text of 0 and 0x01, the value to else, set the value to 0. Remember, you are measuring the voltage at the input to ChipWhisperer, which is measured across a shunt resistor. The end result of this is that a lower voltage actually means more power. So you might see the spikes flipped from the expected direction to based on a 1 taking more power than 0. We're going to try adding in this for loop. Obviously, it looks a little bit different. I'm not really sure I understand like the Python code that well, or how the modifications like what the difference in that graph really means at the end of the day. I mean, it appears to have much smaller fluctuations in the power. The graph now appears to have smaller fluctuations in the spikes, except for the beginning initially. All right, so the strong spikes right at the beginning plus the weaker structure later is exactly what we would expect. You're seeing a clear leakage event when forced bytes are first processed, and much smaller detectable leakage later because the Hamming weight contrast. The lab's original setup forces a plain text byte, which gives a Hamming weight difference The byte is processed very early in the AES round structure, so its effect shows up near the beginning of the trace, where the difference of means has a larger spike. Even after you tweak the experiment, if that early operation still includes a large Hamming weight change, that first region keeps a strong spike because of the power difference between the two classes is large there. So the early part of the trace is still where big, obvious operations happen on a controlled byte, and they dominate the difference plot. The rest of the trace looks weaker. Several factors reduce later spikes. Smaller Hamming weight differences. You switched from all zeros and all one to closer values. The difference between the Hamming weight differences shrinks from 8 to 1. So the corresponding power difference is much smaller, more noise and more overlapping activity. Later in the trace, many AES operations overlap. The effect of one byte's Hamming weight difference is diluted among other switching activities, so the difference of means curve flattens out. Finite number of traces. With fewer traces, random noise does not average away as well, so the small, true effects later in time may be buried under noise. What we can try next, increase n, number of traces, while keeping the smaller Hamming weight difference. If you double or quadruple n, small spikes later, and the trace should become a bit more distinct as noise averages out. Compared to experiments on the same plot, run once with all zeros and all ones, save diff large, run again, say with 0x07 and 0x0f, small difference. So it's given me some code, but I'm not sure the best way to implement it. Capture traces with your chosen experiment, group traces into classes, compute the two averages, plot the difference. Yeah, but it's giving me multiple different kinds of variants, and I'm not sure which. Giving me more variants, and I'm not sure if it wants me to include different cells. So I'm asking it to clarify I should include more cells, or how exactly I should run these different variants side by side. So this was the original. And it's thinking, thinking, thinking. Still thinking. Doesn't like that question. Right now, your notebook shows a standard lab flow, and you've already modified the capture cell at 15. Oh, I'm just curious, like what kind of modifications I should make here. It's literally giving me the same cell back in this suggestion. The only thing that it has changed here is adding a dot copy, which I'm not really sure what the significance of that is. So it keeps its own copy so that each trace keeps its own copy. Keep this as your main capture cell, but fix the stored plaintext so each trace keeps its own copy. Leave this one as is. Leave this one as an example. It helps show how the grouping condition works. Next, blank code cell group traces. Put this in the first real implementation cell after the example printout. I'm not really a fan of this. New code cell, reusable experiment helper. So I'm going to go ahead and end stream here because I think that I've done most of what I can. And I may need to just kind of dive a little bit deeper into this before I can really share anything of value. Because right now I just kind of feel like I'm spinning my wheels. So I'm going to go ahead and end that stream. Thank you for tuning in. We had successfully completed the large Hamming weight swings, which was pretty short, but